that down. Prediction.
For prediction, Japan had incredibly advanced warning systems. Get this. All 27 Shinkansen bullet trains in the affected area stopped automatically, a full 1 minute and 20 seconds before the main tremors hit.
Wow.
Zero derailments, zero injuries on those trains. Haiti had no such early warning capabilities at all.
Okay. Planning.
In terms of planning, Japan conducts massive annual earthquake drills. Like the Michinoku Alert 2008 exercised thousands of participants. It helped them identify risks, like communities getting cut off. Haiti had no comparable drills or planning mechanisms in place.
And preparation. Building codes, that sort of thing.
Exactly. For preparation, Japan has incredibly strict building codes. Reinforced concrete, resilient designs are mandated. Citizens are educated on how to respond. Emergency services are well-trained, well-equipped. Haiti, by contrast, lacked these measures. That led to widespread building collapse and an overwhelmed, struggling response effort. A huge difference.
Okay, so geology isn't the only source of hazards. The atmosphere plays a massive role, too, bringing things like tropical storms. Our sources even give a quick primer on why different parts of the world get different weather in the first place.
That's right. It all really starts with the sun, fundamentally. The Earth's tilt on its axis and its curvature. These dramatically influence how much solar radiation insolation, basically sunlight, any particular location receives.
Right, more direct sunlight at the equator.
Exactly. And that, coupled with high and low pressure systems, descending air creating dry, calm conditions, rising air bringing windy, wet weather, all that drives global atmospheric circulation. It's often mapped out by the tricellular model.
And that explains global patterns. Rainforests here, deserts there.
Precisely. It elegantly explains why we generally have lush rainforests near the equator and hot, dry desert conditions around 30 degrees north or south latitude. It's all connected.
So with that global circulation in mind, how do those incredibly powerful tropical storms, hurricanes, typhoons, cyclones, whatever you call them, how do they actually get started?
They begin over vast stretches of ocean where the surface water temperature is at least 27 degrees Celsius, and that's the key fuel.
Warm water.
Very warm water. Hot, humid air rises rapidly from the ocean surface. As it rises, it cools and condenses, forming massive clouds and creating an area of intense low pressure down at the surface.
Like a vacuum effect?
Sort of. Air from the surrounding higher pressure areas rushes in to fill this low pressure gap. But then, the Earth's rotation, the Coriolis force, deflects these incoming winds.
Ah, the spinning effect.
Right. It causes them to spiral inwards, creating that characteristic swirling pattern we see from space. The storm keeps feeding on the warm, moist air, intensifying as it typically moves westwards across the ocean. They can grow huge, over 500 kilometers across.
And the structure, the eye of the storm.
Yeah, they have a central, usually calm eye with very low pressure. But surrounding that eye is the eye wall. That's where the most severe weather, the strongest winds, and heaviest rain are found. And then you have the extensive spiral rain bands extending outwards. They finally lose energy and die out when they cross over land.
Why over land?
Because they're cut off from their vital fuel source, that warm ocean water and the moisture it provides.
Okay, makes sense. Now, how does climate change tie into the intensity of these already powerful storms?
Well, our materials indicate that increased global temperatures due to global warming provide more heat energy. That extra heat fuels greater evaporation from the oceans, and that, in turn, seems to intensify tropical storm activity.
So more intense storms, not necessarily more storms overall.
That seems to be the trend the evidence points towards. While the total frequency might not change significantly, though, there's debate on that too. There's compelling evidence that the most intense storms, categories 4 and 5, have been increasing. And predictions suggest they could continue to rise by maybe 2 to 11% by 2100.
And could they affect new areas?
There's also a growing belief, that rising sea temperatures further from the equator could mean tropical storms start impacting entirely new geographical areas that weren't previously at risk.
Let's look at a specific example to bring this home. Typhoon Haiyan in the Philippines. Our sources cover that one.
Yes, November 2013. Typhoon Haiyan. A truly catastrophic Category 5 storm that devastated the Philippines. It brought incredibly destructive 170 mph winds and, crucially, an immense 15-meter storm surge.
15 meters. That's enormous. What were the primary effects?
Immediate and horrific. Approximately 6,300 deaths, mostly from drowning due to that storm surge. 40,000 homes completely destroyed. 90% of the city of Tacloban was just devastated.
And the secondary effects, the ripple effects.
Even broader and longer lasting. You had 14 million people left homeless. 6 million lost their primary source of income. Widespread power cuts hampered rescue efforts. Aid was severely slowed, leading to critical shortages of food, water, shelter, which then led to disease outbreaks and, sadly, looting in some areas.
What were the responses like for Haiyan? You mentioned the contrast with Haiti earlier. Were lessons learned here?
Well, aid agencies did respond swiftly. The U.S. aircraft carrier George Washington helped with search and rescue and aid delivery. 1,200 evacuation centers were set up quite quickly.
International aid came in.
Yes, the UK government sent shelter kits. French and Belgian field hospitals were established. Longer term, plans are made to rebuild infrastructure, provide new fishing boats to help communities recover livelihoods, and importantly, build cyclone shelters in coastal areas for the future.
So what's the takeaway from managing these storms?
What's clear is that proactive strategies are crucial. Consistently monitoring a storm's development and track, issuing timely warnings, running awareness campaigns so people know what to do, and then protection measures. Reinforcing buildings, constructing seawalls, building houses up on stilts, improving storm drainage systems, all vital in reducing the impact.
Right. Now, even here in the UK, we're not immune to natural hazards, especially weather-related ones. Our sources describe the UK as being in the middle of a weather roundabout. That sounds like a recipe for chaos.
It kind of is. It makes our weather famously varied and often extreme. We get air masses from lots of different directions, the Arctic, continental Europe, the Atlantic. So the UK experiences a real range of extreme weather events. We get powerful storms like the St. Jude storm in October 2013, 160-kilometer winds, or the Boscastle flash flood back in 2004.
And bits of hurricanes.
Yeah, remnants of hurricanes often drift across the Atlantic and still pack a punch when they reach us. We also get periods of intense cold weather. Remember the Beast from the East in 2018?
Oh yeah, snow everywhere.
Yeah.
Disruption.
Exactly. Widespread snow, freezing temperatures from Siberia. Then there's prolonged rainfall, which is quite common, leading to events like the big Somerset floods of 2013-2014. And on the flip side, we can experience droughts and extreme heat. The 2003 European drought was huge, caused an estimated 20,000 deaths across the continent. And the UK recorded its highest ever temperature than 38 degrees C in Faversham, Kent.
Tell us more about those Somerset floods mentioned in the sources. What caused them? What were the impacts?
Right, the Somerset floods, December 2013 to February 2014. It was really a combination of factors hitting at once. Firstly, it was the wettest January since records began in 1910. Just masses of rain, 350 millimeters in January and February alone.
Wow.
A relentless series of low-pressure systems kept rolling in from the Atlantic, bringing weeks of wet weather. But critically, high tides and storm surges from the Bristol Channel also pushed seawater up the rivers,
Preventing the rainwater from draining out.
Exactly. It acted like a plug, preventing fresh water from reaching the sea, causing riverbanks to burst. And a major contributing factor, mentioned in the sources, was that the rivers hadn't been dredged for at least 20 years. They were clogged with sediment, which massively reduced their capacity to hold water.
So a perfect storm of factors. What were the impacts?
Severe across the board. Socially, you had 600 homes flooded, power cuts, whole villages like Muchelny completely cut off, residents had to be evacuated. Environmentally, widespread contamination from sewage and farm waste and stagnant floodwater, lots of debris. And economically, the clear-up costs were estimated at £10 million just for the council. Over 1,000 livestock evacuated, local roads, railway lines closed, huge damage to businesses and transport.
Was this just a freak event? Or is the UK's weather generally getting more extreme, as our sources seem to hint? What's the bigger picture?
It's a complex question, definitely. The UK has always had extreme weather, let's be clear. But the research does suggest these events are becoming more frequent than in the past.
What's the evidence for that?
There's clear data. Winter rainfall in the UK increased significantly between 1910 and 2015, especially since the 1980s. UK temperatures have risen by about 1 degree C since 1980. And a warmer Atlantic Ocean basically provides more energy, more fuel for these low-pressure weather systems, which intensifies the winds and increases the amount of rainfall they dump on us.
So what are the predictions looking ahead?
Well, scientists predict rain might become more seasonal, perhaps drier summers, wetter winters. River flow and flood events are generally expected to increase. Higher temperatures will also increase drought risk in summer. But there's also uncertainty. For instance, some models suggest melting Arctic ice could potentially lead to a cooler Atlantic in certain areas, which might actually promote more cold weather extremes in winter.
Interesting. So it's not straightforward.
Not entirely. There's also a theory gaining traction that our weather patterns might be getting sort of stuck more often, maybe due to changes in the jet stream that could lead to longer periods of either drought and heat waves or prolonged cold and wet spells, depending on the season and the pattern that gets locked in.
This inevitably leads us to the biggest picture of all, climate change. Our sources take us way back here. What's the historical evidence that climate has changed over geological time, and then what's changing right now?
Right. If we look at the bigger picture, the Quaternary period, that's the last 2 million years or so, clearly shows cycles of dramatically warm periods and cold ice ages. We track this through various lines of evidence.
Like what?
Well, we have direct temperature records. In the UK, we have pretty accurate records going back to about 1650, and they show a noticeable warming trend, especially recently. We also use ice cores. Scientists drill deep into ice sheets in places like Antarctica and Greenland. The trapped air bubbles inside the ice are like tiny time capsules of the ancient atmosphere.
Yeah.
It allows us to reconstruct past temperatures and greenhouse gas levels going back hundreds of thousands of years. And then there's fossil evidence. Finding fossils of animals or plants that only live in specific climates tells us what the climate was like in that place long ago. Like finding hippo bones, basically African animals in Trafalgar Square from 110,000 years ago, tells you it was much warmer then.
Okay, so climate has always changed. What about right now? What's the evidence for current change?
More recently, in our own lifetimes really, we see unequivocal evidence. Polar ice sheets and glaciers are melting at an accelerated rate globally. Glaciers are retreating almost everywhere. We see distinct seasonal shifts, spring arriving earlier, winters tending to be milder, which significantly affects wildlife, migration patterns, plant life cycles, and crucially, sea levels are rising. The data shows about a 0.19-meter rise, that's 19 centimeters, between 1901 and 2010.
Why are sea levels rising?
Two main reasons. Partly from the meltwater running off shrinking ice sheets and glaciers, adding water to the oceans, but also, significantly, due to thermal expansion. As ocean water warms up, it literally expands and takes up more space.
So is this current rapid change just natural variability, or are humans playing a significant role? What do the sources say?
Our sources detail both natural and human causes, and it's important to understand both. Natural causes include things like Milankovitch cycles. These are long-term, predictable variations in Earth's orbit and tilt that affect how much solar energy we receive over millennia.
Okay, long-term cycles. What else?
Fluctuations in solar activity, like sunspots. Periods of low sunspot activity, like the Maunder minimum during the Little Ice Age between 1645–1715, seem to correlate with colder periods on Earth, and volcanic activity plays a role too. Large eruptions, like Mount Tambora in 1815, blast huge amounts of ash and sulfur dioxide into the stratosphere. This can reflect sunlight and cause short-term global cooling. Tambora led to a 0.7 degrees C temperature drop, causing the infamous year without a summer in 1816. Crops failed globally. However, volcanoes also emit CO2 over the long term, which is a greenhouse gas and contributes to warming.
Okay, so there are natural drivers. But what about the human contribution?
This is where the sources really emphasize the current situation. They highlight what's called the enhanced greenhouse effect. The profound takeaway here is that while natural cycles cause climate to ebb and flow, humanity's current footprint, mainly since the Industrial Revolution, has created this enhanced effect. It's like we've thrown an extra blanket over the planet, accelerating warming far beyond natural variability.
How are we doing that?
Primarily through increased emissions of specific greenhouse gases. CO2, carbon dioxide, accounts for about 60% of this enhanced effect. It comes mainly from burning fossil fuels, coal, oil, gas, plus deforestation and vehicle emissions. Then there's methane, CH4, about 20% of the effect. Sources include livestock farming, rice paddies, and gas leaking from landfills and pipelines, and nitrous oxide, N2O. It's present in smaller amounts, but is incredibly potent, about 300 times more powerful than CO2 at trapping heat. Comes from sewage treatment, agricultural fertilizers, and power stations.
So these gases trap heat.
Exactly. They let sunlight in, but they trap the infrared radiation, the heat that's reflected back from Earth's surface, preventing it from escaping into space. Hence the blanket effect.
Yeah.
And based on current trends, scientists predict global average temperatures could rise somewhere between 1.8 and 4.0 degrees C before the year 2100. That's a huge change in a short time.
What does that kind of temperature rise actually mean for us? What are the predicted impacts if these changes continue?
The impacts are really far-reaching and potentially devastating across the globe. They include likely stronger and perhaps more frequent tropical storms, as we discussed, increased occurrences of severe droughts in some regions, and more intense rainfall leading to floods in others, expansion of deserts, desertification, and significantly rising sea levels, which pose an existential threat to low-lying island nations like the Maldives, Tuvalu, and major coastal cities worldwide.
And impacts on food.
Yes, profound changes to agriculture, Our ability to grow essential crops in traditional regions will likely shift, potentially leading to global food security issues. Weather patterns become less predictable for farmers.
Given all these risks, earthquakes, volcanoes, storms, climate change impacts, why do people still choose to live in these hazardous areas? Seems counterintuitive.
That's a really pivotal question, isn't it? And our sources explain it's often a complex mix of reasons. For some, particularly in poorer parts of the world, there's simply no other economic choice. Poverty forces them onto marginal, often riskier land.
But others have a choice.
Yes. Some might perceive infrequent events, like a volcano that erupts every few centuries, as less of a direct, immediate threat. It won't happen in my lifetime thinking. Others might feel safer now due to better monitoring and warning systems, especially in more developed countries. There's a sense, perhaps sometimes misplaced, of being protected.
And are there actual attractions to these areas?
Definitely. There are tangible benefits. The fertile volcanic soil is great for farming, as are river floodplains, despite the risks. You often find valuable mineral deposits associated with volcanic activity or tectonic boundaries. Geothermal power is another big one. Think of Iceland's Blue Lagoon, powered by geothermal energy. And even tourism. People are drawn to dramatic volcanic landscapes, geysers, hot springs, so there are economic pulls as well as pushes.
Okay, so we understand the risks, why people live there.
Mm.
What can we actually do about all this? Our sources talk about two main approaches: mitigation and adaptation. How do these strategies work?
Precisely. They represent two different but equally vital strategies for tackling the challenges, particularly climate change, which exacerbates many hazards.
Let's start with mitigation. What does that involve?
Mitigation focuses on tackling the root causes of climate change, primarily by reducing greenhouse gas emissions. One approach is employing carbon capture and storage, CCS. This involves capturing CO2 emissions, say from power plants or industrial facilities, and injecting them deep underground into stable geological formations.
Storing the carbon away.
Exactly. Another key strategy is planting trees or reforestation afforestation. Trees naturally absorb CO2 through photosynthesis. The sources mention the UK invested £25 million in Brazilian reforestation efforts, for example. A fundamental shift is towards alternative energy production, moving away from fossil fuels to renewables like hydroelectric, solar, wind, nuclear, and tidal power sources that produce little to no carbon emissions.
And getting countries to work together.
Absolutely critical. International agreements are vital for mitigation. Things like the 2005 Kyoto Protocol, the 2009 Copenhagen Pledge, and more recently, the legally binding 2015 Paris Agreement, where 195 countries committed to taking action to limit global warming.
Okay, so mitigation reduces the cause. What about adaptation?
Adaptation focuses on adjusting to the climate change impacts that are already happening or are now considered unavoidable, even if we mitigate successfully. It's about coping with the new reality.
How do we adapt?
Well, for example, reducing risk from rising sea levels. This involves practical measures like building higher and stronger seawalls. The Maldives are building walls up to 3 meters high in places, using sandbags for temporary defenses. It can also mean raising the level of land or buildings in vulnerable areas, or in extreme cases, planning for the managed relocation of populations away from coastlines that simply can't be defended.
What about farming and water?
Big areas for adaptation. Adapting farming practices might mean changing what crops are grown. Maybe colder climates become suitable for wheat, while the UK might be able to grow more Mediterranean crops like olives or citrus. It also means altering planting and harvesting seasons, developing drought-resistant crop varieties, and increasing irrigation in areas facing water scarcity. And managing water supplies becomes crucial. Our sources mention innovations like creating artificial glaciers in Ladakh, India, diverting meltwater and freezing it during winter to provide water in the dry season. Or urban strategies, like London's water strategy, which includes promoting water-efficient devices for homes and businesses, and even considering desalination plants, like the existing one at Beckton on the River Thames, to turn estuary water into drinking water.
So mitigation tries to stop it getting worse. Adaptation helps us live with what's already changing.
That's a good way to put it. We really need both working in tandem.
Well, from the grinding plates way beneath our feet to the swirling weather patterns high above our heads and grappling with the huge, overarching challenge of a changing climate, we've taken a truly comprehensive deep dive into natural hazards today.
And we really have.
And it seems clear that while these events themselves are natural phenomena, our human vulnerability, and crucially, how we plan for them, prepare for them, and manage their impacts. That makes all the difference.
It really emphasizes that point, doesn't it? Knowledge isn't just about understanding the what and how of these events, but also profoundly understanding the why it matters to us. The sheer interconnectedness of the geological system, the atmospheric system, and our human systems means that getting to grips with climate change is absolutely critical to accurately understanding and addressing future hazard risk.
So what does this all mean for you listening? As you go about your day, maybe take a moment to consider the profound impact of our interconnected world. And think about the immense difference that proactive planning, robust preparation, and those innovative solutions we talked about can make when facing these powerful natural forces.
Which leaves us with a final, maybe provocative thought for you to ponder. In a world where hazards are both ancient forces and rapidly evolving threats, what role do you think our individual choices and our collective global cooperation ultimately play in shaping our future resilience?